Hey, welcome back to ECE 382. Kevin By here. We are moving into Module 13 timers. So this is going to be similar to the SysTick timer, but it's going to have a little bit more functionality, and we're going to use it a lot different. So let's talk about the two uses of timers that we're going to use. First is periodic interrupts, and second, again, is pulse width modulation. And the benefit that we have using timer A and these different timers versus the SysTick timer is that our SysTick timer still created loops in the background, and that is not what we want. So when we wanted to divide and create a 48 megahertz timer, no big deal. That's easy with SysTick. That's what we got there. But once we started looking at any other subdivisions of that 48 megahertz, that's when we started having some issues with the loops and software blocking. And so timer A provides us a lot of capabilities to do different levels of timers without having to software block. So these are all done in the background. So we're going to use something called SMCLK, which is it is 1/4 your system clock. So if we are operating typically at 48 megahertz, these timers are going to, if we're using the SMCLK, it's going to automatically be at 12 megahertz. So it's already cutting down our time a bit. There's two additional, so that's not really a divider, that's just the clock we're going to use. But there's two stage clock divider that we can use as well. So the first one coming from the register ID will divide by 1, 2, 4, or 8. And there's another coming from the Tidex, which is another divider, which is going to allow us to divide again. So if we wanted to divide by, say, 8, we would take our ID, set it equal to 8, and our Tidex, and set it equal to 1. And now we have a 12 megahertz divided by 8 counter. That's going to still be counting just like SysTick. It's going to tick at this rate now. And so instead of having SysTick, which is always ticking at 48 megahertz, and we just divide how we get those, how we use those ticks, this timer is now going to be ticking at a much slower rate. So SysTick counted down always. Timer A can count up or down. It can also count up and down, so it'll count up to a value and then down from a value. It can count to its largest number and then go back to 0. We can set it or clear it in software. We can use it to generate interrupts just like we did with the SysTick, but this has a lot more functionality. It's a 16-bit counter, which means our precision is 2 to the 16, so that's how high we can count. And we're counting again at this rate that we set the clock. And there's two functionalities that we'll use: input capture, which allows us to capture a value at a certain rate. So say we want to capture something at 10 hertz. If we want to look at the value of a sensor at 10 hertz, we'll use input capture, or we will use output compare. And what that allows us to do is wait until our counter is equal to some value and then do something. So today we're going to be focusing here with the output compare, and we'll talk about a little bit more information about what that means this time, and then next time we'll look into input capture a little bit more and see what that is. So these are a number of the registers that correspond to timer A. This guy here, TA, let me get a smaller pen, bring out the rainbow pen, TA0R. That is timer A0, and that is the counter. So that's going to be the value that's going to be counting as we go through this. And then these 7 registers here are our compare registers. These are all timer A0, so there's multiple timers. Timer A has 4 different timers, timer A0, 1, 2, and 3. And each one of those has a number of registers that we'll compare to, so or capture data into. So if we want to, basically our counter will count depending on if we're counting up or down, and it will compare it to what's in CCR0, and if those are equal, then something will happen. So an interrupt will occur most likely. So those are the 2 important ones to remember: timer A0R and timer A0 CCR0, which is pretty self-explanatory there. Here's those clocks and prescales I talked about. So SMCLK, we're going to set that or select that clock. Again, that's a standard clock that is just our system clock divided by 4. So again, 48 megahertz divided by 4 is SMCLK. So remember, this is where we start. That's going to be our first clock. And then we can prescale it here, and then again the TAIDEX, and we'll see this register as well. Allows us to divide by 1, 2, 3, 4, 5, 6, 7, and 8. All right, so why do we care about dividing? This comes down to what is our requirement. So for example, if I wanted to count to 100 milliseconds, so my goal is I want a 100 millisecond counter, so it's going to, every 100 milliseconds, something's going to happen, and say I will turn on an LED every 100 milliseconds. And the way I'm going to do that is I'm going to have timer A count for me in the background, and every time it gets 200 milliseconds, it's going to turn off the light or toggle the light, basically. So if I had just decided to use a 12 megahertz clock, would I be able to? So if I just use SMCLK, again, which is 12 megahertz, so that means that I'm counting from 0 to 2 to the 16th, which 2 to the 16 is equal to 6, 5, 5, 3, 6. So, I have 16 bits here. So this is bit 15 all the way down to bit 0. And all that's happening is I go 0, 1, 1, 0, 1, 1, 1, 0, 0, and I just count. I'm counting. And the rate that counter is counting is based off of our clock and scaling. So if I'm counting at 12 megahertz, and I can only count up to 65,536, what is my range of, what is my time range that I can count? And we can use an equation. Range equals our resolution times our precision. And our precision is going to stay constant with our timer A at 2 to the 16, or 6, 5, 5, 3, 6. I don't know what that little comma was. And then our resolution here, 12 megahertz, or 1 over 12 megahertz, or 83.33 nanoseconds. And if I multiply those together, I get a 5.5 milliseconds. So, as we can see, I'm never going to be able to count, have my hardware or my timer A, which is counting in the background, get to 100 milliseconds, because with a resolution of 12 megahertz, I only get 5.5 milliseconds. So I have to slow down the clock even further, and I do that with the prescale and the timer. So let's slow down the clock. We can divide by 4, and we can divide by 6. That's going to give us overall 12 megahertz divided by 6 times 4, or 24 obviously, which allows us to get 2 microseconds. Okay, so that's not my new resolution. So every time it takes me 2 microseconds to count from 0 to 1 to 2 to 3 all the way to 65,536, which is much slower than 83.3 nanoseconds. But when I do the math, I do 2 microseconds times 65,536. That equals 131 milliseconds, and now I am good to go. Rainbow pin comes out, we're happy. Check. So that's why we use these prescale in clocks dividers, so that we can get to a division in a value that we want to count to. And that's where the engineering comes in. How do we use this 48 megahertz clock? We can then use the SMCLK to get that down to 12 megahertz, and then we can prescale that from there to get where we need to go. All right, let's talk about output compare. So basically, it's a mechanism to cause a flag to be set and an output pin to change when the timer matches a preset value. Okay, so that's output, so we're affecting the output, and we're comparing our timer to a preset value. And the other benefit, the output compare could also output compare event can also trigger an interrupt. So we're going to do both of these in the lab. We're going to use our output compare to toggle the values going to the motor. So in previous motor labs, so your motor simple, you set it to 1, you waited, you set it to 0, you waited, you set it to 1, you waited, in that loop, the for loop, went on forever, right through until the time was up or it hit a bumper. Okay? But with the output compare, we can automatically, without having to do any logic, set up a timer and a preset value, which, hint, is going to be somewhere along the lines of duty cycle. And what it's going to do then is, depending on the out mode we choose, which we can see here we have this toggle reset value, which is the one we're going to use, which is basically going to allow us to, at a certain rate, duty cycle, turn on the bit, turn off the bit. And all we have to do to set this up is set up the right timer, set up the duty cycle or the period that the timer is going to operate at, and then set up the compare value. And that's what we're going to see with the CCR0. And that's pretty much it. So pretty cool. And then the other benefit is the output compare event can also trigger an interrupt. This is how we're going to start. We're going to take our bump sensors to the next level. Instead of just checking them at random points in our code, we're going to periodically check them. Still not the best, because a bump sensor we want to react to immediately. So a periodic interrupt is still not the best, but we're just taking baby steps to get where we need to get. So we're going to, at a certain rate, check the bump sensors and see what they're doing. All right, and then there's four more modes to count. Obviously, stop, don't count. Up mode, we just count up to the value we're looking at. And up down mode, which is going to count us to a certain value and then back down to 0. And we're going to see this for our pulse width modulation and this here for our periodic interrupt. Okay, so a lot of this is just setting up the clocks beforehand. This isn't a lot of design. You don't have to make a clock. You don't have to program the clock. All that's going to be done for you, but what you do need to do is set up the registers correctly so that the clock operates how you would like it. So to do that, I'm introducing a number of registers. All of these are in that main the MSP 432 guide. It's the same one we've used for SysTick and others. This is under timer A of that guide, and that this will be provided to you for GRs. So these tables will be there for you to use during the second GR. So what I recommend is pulling up that guide, and let me just grab the name real quick so that I don't forget. But it is in your starter files underneath data sheets. Then it is the SLAU 356H. SLAU 356H.pdf. So what I recommend, if you want to use your Squadron printers, just go in there, print the timer A section, have that with you while you're working on these. That way you get familiar with them, and then you can use them when you are coding, and then when you have the GR next, sometime at the end, near the end of the semester, then you get familiar with this beforehand. All right, so timer A1 init. This is going to be in the timer A1C file, and it's going to be one of the first. Well, actually, we're going to do this second part of the lab, but I just want to introduce it first because this is the periodic interrupt concept. That's a lot easier. But concept here, check the bump sensors at 100 Hertz. Oh, look, we just did some math here to figure out what we needed to do to get a 100 millisecond timer or counter, 100 milliseconds, 100 Hertz. So we need to get our system clock down to 83.39 seconds. So that's going to be a divided by 6 and a divided by 4. I said we need it up mode. So let's get some of this together. So the first thing we need to do is halt the timer. It's always good to just halt things before you try to change all the settings, which is MC equals 0. Okay, so what that means is when we're looking at this register, so if I want to get into code, I'll do code in this cool gray. I'm taking timer A1. I'm taking, that's a 1, the CTL register, and I'm clearing MC. MC is bits 5 and 4, so if I take 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there's 10 through 15. All I care about right here are bits 4 and 5, and so 0, 1, 2, 3, 4, 5, and I'm clearing them, so I'm going to AND equals 0x0030. That's going to give us, that's going to clear these 2 bits, and it's going to then stop the timer, halt the timer, so that we can then update the settings. All right, so let's look at prescale. So we said we have to do divide by 4 and divide by 6. Well, we have the divide by 4 here, which means we need a 1 and a 0 in bits 7 and 6. So just so I can keep track of where I am. So I need a 1 and a 1 here. So set the time. Set timer and prescale. So I want ID equal to divide by 4. And I want the timer select equal to SMCLK 10. That's bits 9 and 8. Oops. So I want 10. Bits 9 and 8 are 10. And now that gets me those. So I'm going to set timer A1 CTL equal to 0x280. So we got our 2, our 8, and our 0. Alright, so that's the first 2 steps. So we've halted the timer. We set which timer we're using. We're using the CMSCLK source clock. And we've now divided it by 4. Not quite there. Still got a lot of work to do. Alright, so next step. Alright, so we said that we want to use output compare. And to do that, we're going to set module 0. So like I said, there's a number of these modules. So the one we're interested in is timer A. This is actually timer A1. So we're using timer A1 CCR 0. So if we go into the CCTL guy here, that one I want, yes. So this is going to be, so set module timer A1 CCR 0. Yep. To compare. And then we're going to arm the interrupt. Alright, so to set it to compare, we're going to actually take CCTL0, which is part of module 0. That's the control of module 0. And we're going to set it to compare mode, which is bit 4 here. Or sorry, this is going to interrupt enabled. And if we wanted it in compare mode, right there, it's all zeros. So we're going to arm the interrupt, and we're going to set it to compare mode, which is all zeros. So not very exciting, but that's going to be CCTL. And again, it's always timer A1 arrow CCTL 0, and that's going to be set equal to our all zeros. We got a 1 here, and then the rest are zeros. So that gives us, so bit 4 is a 0, everything else is, or sorry, bit 4 is a 1, everything else is a 0. That gives us 1 0. Okay. All right. So now we're going to set it, we're going to actually set our compare value. So now this is really setting our CCR0. So basically what this was allowing us to do was compare arm interrupt, and now we're going to actually assign compare value. All right, let's just start that over. Assign compare value to CCR0, which is our going to be how often do we want our periodic interrupt to run, and that's going to be based off our period. So again, we always minus 1 because we're counting down to 0. So we just get timer A1 CCR0, and that's going to be equal to period minus 1. All right, and that's going to then take this period value. It's going to store it into our CCR0 here, which is our capture compare value. So that's just going to be when our clock's counting. That's what it's going to be counting, comparing that value. So, hey, if that value is, we're trying to get to 100 megahertz, then that's going to be what we're going to use. But it's not going to be 100 megahertz. We'll talk about that here in a minute. All right, configure input clock divider. So we said we needed 4 and 6. We've only done 4 so far because 6 is in a different register. 6 is in the EX0 register because that's just where it is. So configure input clock divider. And we said we want to divide by 6, so we need 101. So that's just going to be timer and this is all timer A1, it's all caps, EX0, that's equal to 0x0005. Alright, so now we have our divider. We divided by 4 previously, now we're dividing by 6. 4 and 6. And we were already at 12 megahertz, so we took 12 divided by 24 and got us that 83.33 nanoseconds, 2 microseconds, which gives us our 131 millisecond counter. All right. So the last thing we have to do, and since we are calling interrupts, we have to tell the nested vector interrupt controller, which is in charge of handling all interrupts on the MSP432, what priority this interrupt has. And the way we do that, so we are using timer A1. Let me get the highlighter. Holy moly, that's giant. A tiny highlighter. And we're using module 0, so we're going to grab this guy right here. That's going to tell us a few things. Okay, so first off, it's going to tell us that this is interrupt 10, and it's part of the nested vector interrupt controller processor 2 with a priority 2. And so if we go down, and so the first thing we need to do is take a look at our IP2 register. We're in priority 10, and we're going to set it with a priority of 2. So if I take my nested vector interrupt controller, I take IP2, sorry, NBIC IP2, and I have to select these bits because that's the ones that these. So this is priority 10, which is our timer A10 module. So we take that. We're going to take bits 16 through 23, which are, if we just break these up into we got 8 bytes here, 8 bytes here, 8 and 8. So I just take and clear those 2 bits. Those 2 bytes right there. And we're going to set that equal to our priority, which is going to be priority 2. So we're going to OR that. So we're going to take all of that, we're going to OR it. So we've selected this byte, we've cleared it, and now we're going to set it to a priority 2. Which, if we look at the priority of interrupts 10, we're only concerned with bits 16 through 23, and we set it equal, or we OR it with 4, which gives us that priority that we're looking for. So that's a little abstract. A lot going on there. Key things here, we have to look at the IPR2 register to figure out where we need to clear. So if I was looking at TA20, I'd have to probably look at IPR3. We can see that here, IPR3. So we're going to have to look at a different table. It's going to tell us which bits we have to clear from those. And then the priority lives in bits 21 and 23. So we take bits 21 and 23 down to 21, and we set 4 in there for a priority of 2. All right, the next thing then is we just need to enable that interrupt. To do that, we look down at this guy here, the ISER 0. Again, the 0 just means which module. Remember, there's a number of modules. We can see those all here. So you can go from 0, 1, 2, 3, 4, and so on and so forth. But we're working with module 0 for this one. We'll work for different ones with the periodic or with the pulse width modulation. All right, so next step is enable the interrupt, which we're going to do using the NVIC ISER 0. So this set the priority here. We're going to enable interrupt here. We can see writing a 0 has no effect. Writing a 1 enables the corresponding interrupt. So I need to enable the interrupt, which again is the 10th bit because it's the 10th interrupt, which if we look at that is going to be that value. That's the 10th bit. So 10th bit because IRQ equals 10. All right. So yeah, a lot of stuff going on there. Last thing we do is we reset the timer and start it in up mode. So if we go all the way back up here, we look at our CTL. We reset the timer. So timer A clear. We're going to set bit 2 to a 1. Then we're going to start it in up mode, which is 1 1. So if we look at that, that's going to be 1 1 1 0 1 0 0, which is, I believe, 0x. Just double check that. Yep, 0x14. Okay, so way back down here, we're going to reset the timer and start in up mode, which is timer up mode, which is timer A1 CTL equals 0x0014. And then the last thing, we have to enable interrupts. We'll do that in main with a function call that allows everything to happen in main. All right, a few things just to finish up here. Timer A1 stop, so that we can stop the timer. Again, that's just, I'm just going to assume you know that timer A1 goes to the beginning of this. CTL, that's again going back and halting the timer. And then we're going to disable the interrupt so that our nested interrupt controller knows that we are done. And again, remember, when we write a 1 to the interrupt, nothing, it activates it. If we write a 0, nothing's going to happen. But if we read the current state, it's going to, sorry, we need to reset the ISER 0, which is basically just reading from it. Which is the same thing we did before, except, yeah, sorry, I forgot the 0. So we'll check that I did that one right. Yep, cool. All right, so that's that. The last thing is now we need to tell it what to do and where to call our function. So the way we're going to do this is when we call our timer A1 init, the input to our timer A1 init is going to be a pointer to a function. And the way we do that, it's going to be so there's a function that takes in no values and returns returns no value. So that's going to be our void. Or sorry, that's going to be our function. So we're going to assign which is a global variable. You'll see that in the code. So a global pointer to the function. And then when every time, and if we look at this interrupt list here, every time this interrupt occurs, the IRQ handler is going to get called. And our IRQ handler, all it's going to do is acknowledge the interrupt by clearing. So we clear this 1 right here. If we go back up to CCTL, which is this guy here, 0, no interrupt pending. We're going to clear the interrupt because we're about to take care of it. And then we're just going to call our timer A1 task, which has no input, and then we're done. So clear interrupt. Call ISR, interrupt service routine. Don't forget that value, or name. All right, so that's pretty much it for timer A1 as a periodic interrupt. This is what you're going to do through the pre-lab. You're going to get this set up. Hopefully all that made sense. Again, I highly recommend you look at the document sheets, the SLAU356H.pdf. It starts making a lot more sense when you start reading these, looking at these tables. These tables, again, will be provided to you during the GR, but it's beneficial if you've seen them before. We're going to take a break and then work into the next video, which should be significantly shorter, but it will go over the pulse width modulation and how we're going to change and run our motors.